Welcome back to this course, Eigenvalues and Eigenvectors. In the last session, we have seen what is the definition of eigenvalue. The eigenvalues, which is nothing but the roots of the characteristic polynomial. Okay. Now, in this lecture, we are going to see how to find the eigenvectors of a given eigenvalue. Right. Now, as we know that the eigenvalues, which are nothing but the roots of the characteristic polynomial, and the definition says that the eigenvector, which is the non-zero solution of a homogeneous system, A minus lambda I into x equal to 0. So very well we can see that if x equal to 0, it will satisfy the system, but our interest is to find the non-zero solution capital X such that it's satisfying the given system of equations. Now let us start with a simple problem. Find the eigenvectors of the 2 cross 2 matrix. The entries are 2, 1, 0, 3, right. Now the characteristic equation of the above matrix is lambda square minus 5 lambda plus 6 equal to 0. And then the roots of the polynomial are lambda 1 equal to 2 and lambda 2 equal to 3, right. Now let us assume that x equal to x1 comma x2 be the vector such that a minus lambda I into x, which is equal to 0. This capital X is your eigenvector. We have to determine. Now let us assume the first eigenvalue lambda 1 equal to 2, then replace lambda equal to lambda 1 in the matrix equation. See, therefore we are getting a minus lambda 1 into I into capital X equal to 2 minus 2, because lambda 1 equal to 2. See, therefore 2 minus 2, 1, 0, 3 minus 2, and the vector x1, x2 equal to 0. Okay. So if we solve this equation, if you see that first term gives 0, the second term is 1, and here it is 0, here it is negative 1. See, therefore what it says, x2 equal to 0 or minus x2 equal to 0. See, therefore x2 is 0, and then x1 can be anything. So if we are coming to the situation like this, anything can be, any variable can be anything, means we have to assume that that variable equal to 1. Okay, it is our choice. So let us assume that x1 equal to 1, and already from the above equation we got x2 equal to 0. See, therefore the first eigenvector is 1, 0, corresponding to the eigenvalue lambda 1 equal to 2. Now let us take the second eigenvalue lambda 2 equal to 3, then replace lambda 2 equal to 3 in this. See, therefore 2 minus 3, 1, 0, 3 minus 3, and the vector is x1, x2 equal to 0. Therefore we are getting minus 1, 1, 0, 0. See, therefore minus x1 plus x2 equal to 0. That gives x2 equal to x1. Okay. So what it says, there is only one equation, but there are two unknowns. See, therefore this system of equation having infinite number of solutions. Among them we are going to choose one. So x2 equal to 1, and then x1 can be anything. See, therefore let us assume that x1 equal to 1, then x2 equal to 1. See, therefore the second eigenvector is 1, 1. Okay, right. Look at this. These two vectors are non-zero vectors, right? What is our x1? x1 equal to 1, 0. And x2 is 1, 1. These two are non-zero vectors which are satisfying the above system of equations. Right. Now let us see the non-trivial example. Why I am saying non-trivial example? In the last example, first thing is it is a 2 cross 2 matrix. That too, the matrix is upper triangular matrix. See, therefore, from the above lecture, we see that the eigenvalues are which are nothing but the diagonal elements of the upper triangular matrix. Look at this, 2, 3. Whereas in this matrix, all the entries are non-zero. It is not upper triangular, it is not a diagonal matrix, it is not a lower triangular matrix. See, therefore, it is not a simple matrix, it is little complicated one, right? Now from the above experience, we see that the matrix is 3 cross 3 matrix. See, therefore the characteristic polynomial is a cubic polynomial. It will be of the form lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0, where s1 is sum of the diagonal elements, and S2 is sum of the minus of the main diagonal, and S3 is determinant. See, therefore, if you calculate all these things, you will be getting the characteristic polynomial like this: lambda cube minus 4 lambda square plus lambda plus 6 equal to 0. And by using the synthetic division, we can calculate all the roots: lambda 1 equal to minus 1, lambda 2 equal to 2, and lambda 3 equal to 3. Right? We have three distinct eigenvalues. For each eigenvalues, we have to calculate what is the eigenvector corresponding to the eigenvalue. Let us assume that the eigenvector be of the form x1, x2, x3 transpose be the vector such that a minus lambda I into x equal to 0. If lambda 1 equal to minus 1, then your vector, the corresponding vector, let me call this as capital X1, and then the capital X1 is x11, x12, x13. Okay. So therefore, a minus lambda 1 I x1, which is of the form 3, because here lambda 1 is minus 1, so therefore 3 minus of minus 1, that becomes 3 plus 1, minus 4, then 4, 1, minus 2 of minus 1, that is minus 2 plus 1, then 4, 1, minus 1, 3 plus 1 equal to 0. Then if we do that, if we do the calculation, we will be getting two distinct equations: x11 minus x12 plus x13 equal to 0. Then the second equation is x11 minus x12 plus 4x13 equal to 0. Okay. Now there are two equations, but there are three unknowns. See, therefore, again the system of equations having infinite number of solutions. Among them, we are going to choose a non-zero one by using the cross multiplication method. For this, we have to take the two distinct equations, place all the coefficients of the first equation 1, minus 1, 1, and then the coefficients of the second equation 1, minus 1, then 4. To calculate, to find the value of x1, you remove the coefficients of x1, then leaving the, you start with the x2 and x3, then find the determinant of this, that is 1 minus 1. Look at this here: 1 minus 1, 1 4, 1 minus 1 minus 1, 1 4. Similarly, to find the value of x2, first you take this column, and then the second column will be like this. So that is 1 4 1 1. Then find the determinant. Similarly, to find the value of x3, you remove the third column, you take the first two columns. First two columns, that is 1 2 minus 1 minus 1, that gives the value of x13. Right. So what is this? x11 is minus 4 plus 1, that is minus 3. Then similarly 1 minus 4, therefore minus 3. This gives 0. See, therefore this gives x11 equal to minus 3, and x12 equal to minus 3, x13 equal to 0. If there is any common factor between all these three values, you remove the common factor. In fact, the common factor is minus 3. See, therefore if you remove the common factor, then it leaves 1 1 0. Right. See, therefore the first eigenvector is x1 equal to x11, x12, x13, that is 1 1 0. Right. This is corresponding to the eigenvalue lambda 1 equal to 1. Right. Now let us take the second eigenvalue lambda 2 equal to 2 and replace lambda 2 equal to 2 in the matrix equation a minus lambda 2 I into x2, where x2 is x21, x22, x23. Okay. See, therefore we are getting these equations: x21 minus 4 x22 plus 4 x23 equal to 0, and the second equation x21 minus x22 plus x23 equal to 0. Again, by using the cross multiplication, we are getting x21 by 0, x22 by 3, and x23 by 3. See, therefore x22 equal to 0, x21 equal to 0. Okay, x21 equal to 0, x22 equal to 3, and x23 equal to 3. There is a common factor. After removing the common factor, we are getting x21 equal to 0, x22 equal to 1, and x23 equal to 1. See, therefore this is the second eigenvector corresponding to lambda 2 equal to 2. Right. Next we take the third eigenvalue lambda 3 equal to 3 and then replace lambda equal to 3 in the matrix equation. Therefore, we are getting this matrix. Here we take x3 which is equal to x31, x32, x33. Okay, see therefore we are getting two equations 0 x31 minus 3 minus x32 plus x33 equal to 0, and the second equation x31 minus 5 x32 plus 4 x33 equal to 0. By using the cross multiplication, we are getting x31 divided by 1 equal to x32 divided by 1 and x33 divided by 1. See therefore x31 equal to 1 and x32 equal to 1, x33 equal to 1. Hence the third eigenvector is this. Okay, right. Now let us see the properties of eigenvectors. The first property, if all the eigenvalues lambda 1, lambda 2, lambda 3 and so on lambda n are distinct, then the eigenvectors corresponding to lambda 1, lambda 2, lambda n are linearly independent. That means if x and y are linearly independent vectors, then alpha x plus beta y equal to 0 means, which implies alpha equal to 0 and beta equal to 0. Okay, so this is a definition of linearly independent vector. Right, then the matrix A and A transpose have the same eigenvalues. If A is a square matrix, then A and A transpose having the same eigenvalues. That is the second property. Third property is product of all the eigenvalues is the determinant of A. That is, determinant of A is nothing but lambda 1 into lambda 2 into lambda 3 into and so on lambda n. Okay, there is a third property. See, look at this. See, finding the determinant of A, it is very difficult problem if the size of the matrix is bigger and bigger. Whereas if you know the eigenvalues of the matrix, then it is easy to calculate the determinant, right? Then the fourth property is, if lambda 1, lambda 2, lambda n are the eigenvalues of A, then k lambda 1, then k lambda 1, k lambda 2 and so on k lambda n are the eigenvalues of k into A. What is k? K is a scalar. Suppose if A is, say for example, A, B, C, D, and then our Ka, which is nothing but Ka, Kb, Kc, Kd. Okay, element wise we have to multiply the scalar. Then another important property is, if lambda 1, lambda 2, lambda n are eigenvalues of A, then lambda 1 power p, lambda 2 power p, lambda n power p are the eigenvalues of A power p, where p is positive integer. Where p is positive integer, right? Then another important property, if lambda 1, lambda 2, lambda n are non-zero eigenvalues of the matrix A, then 1 by lambda 1, 1 by lambda 2 and so on, 1 by lambda n are the eigenvalues of A inverse. Okay, these are all important properties. Let us see one or two problems based on these properties, then we'll go to another topic. First example, find the sum and the product of the eigenvalues of the matrix A, where A is, the first row is 1, 2, minus 2, 1, 0, 3, minus 2, minus 1, minus 3. What is the sum of the eigenvalues? Sum of the eigenvalues, which is nothing but the trace of the matrix. Okay. And then the product of the eigenvalues, which is nothing but the determinant of the matrix A. Okay. For this, let us assume that lambda 1, lambda 2, lambda 3 are the eigenvalues of A. Then lambda 1 plus lambda 2 plus lambda 3 equal to the trace of the matrix A. That is 1 plus 0 minus 3 equal to minus 2. That is the sum of the eigenvalue. And the product of the eigenvalues, which is nothing but the determinant of A. In fact, the determinant is minus 1. Right. Let us see the next example. If 2 and 3 are eigenvalues of the matrix A having the elements 3, 10, 5, minus 2, minus 2, minus 3, minus 4, 3, 5, 7, then find the eigenvalues of A inverse and A cube. Let us assume that lambda 1 equal to 2 and lambda 2 equal to 3. We don't know what is the lambda 3. By using the property, we are going to find out what is the third eigenvalue. We know that the sum of the eigenvalues, which is nothing but the trace of the matrix. See, therefore, lambda 1 plus lambda 2 plus lambda 3 equal to the trace. That is 2 plus 3 plus lambda 3 equal to 7. So therefore, our lambda 3 equal to 2. That is the third eigenvalue is 2. And we know that if lambda 1, lambda 2, lambda 3 are non-zero eigenvalues of the matrix A, then 1 by lambda 1, 1 by lambda 2, 1 by lambda 3 are the eigenvalues of A inverse. See, therefore 1 by 2, 1 by 3, 1 by 2 are the eigenvalues of A inverse. And another property which you have seen, if lambda 1, lambda 2, lambda 3 are eigenvalues of the matrix A, then lambda 1 power p, lambda 1 power p, lambda 2 power p, lambda 2 power p, lambda 3 power p are the eigenvalues of A power p, where p is a positive integer. By using this property, the eigenvalues of A cube are 2 cube, 3 cube, again 2 cube. Right. See, these are the some basic problems related to eigenvalues and eigenvectors. Next, we are going to see the applications of eigenvalues and eigenvectors to compute the powers of the matrix and then to determine the nature of the quadratic form. For this, we need certain things, some basic definitions related to the matrices. First definition, similar matrices. The square matrices A and B are said to be similar matrices if there exists a non-singular matrix, P such that A equal to P inverse B P. That is, A can be written as P inverse B P, or in other words, B can be written as A into P inverse A P. Both the way we can write. Second definition, the square matrix A is said to be diagonalizable. The square matrix A is said to be diagonalizable if there exists a non-singular model matrix M such that D equal to M inverse A M. That means M is a non-singular matrix, therefore inverse exists. You post multiply M inverse and then pre-multiply by M inverse and post multiply by M to A, that gives a diagonal matrix D. Right. Then the third definition is the square matrix A is said to be orthogonal matrix if A into A transpose, which is equal to A transpose into A, which is equal to the identity matrix I. Next definition, a square matrix A is said to be orthogonal if A transpose equal to A inverse. Next definition, a square matrix A is said to be orthogonally diagonalizable if there exists a non-singular orthogonal matrix capital N such that D equal to N transpose A N. Okay, these are all some basic definition. Next, we are going to see how to find the diagonal matrix by using the orthogonal transformation or orthogonal reduction. There are some steps involved. The very first step is we have to calculate the eigenvalues of the matrix A. Second step is we have to compute the eigenvectors corresponding to each and every eigenvalues. That is, we have to compute x1, x2, x3 and so on, xn corresponding to lambda 1, lambda 2 and so on, lambda n. Then the third step is we have to normalize all the vectors x1, x2, x3 by using the formula x1 bar which is equal to x1 upon the length of the vector modulus of x1, x2 bar equal to x2 divided by modulus of x2 and so on, xn bar equal to xn upon modulus of xn. What is the formula for modulus of xn? The modulus of xn which is equal to under root a square plus b square plus c square if our xn which is equal to a comma b comma c. Okay, if xn is having 3 coordinates a b c, then the length of the vector x modulus of xn is under root a square plus b square plus c square. Okay, if we computed all the normalized eigenvectors x1, x2 and so on xn, then we are ready to form a model matrix capital N. The first column of the model matrix is first normalized vector x1, second column is second normalized vector and so on, nth column is nth normalized model matrix xn bar, right? Then you compute the transpose n transpose and an, then you compute d which is equal to n transpose an. After multiplying this, you will be getting the eigenvalues will be placed in the diagonal entries and other entries will be 0. If you do the multiplication like this, n transpose a n, then only in the diagonal entries will be having the eigenvalues lambda 2, lambda 3 and so on, lambda n, all other entries will be 0. That is the beauty of this diagonalization process. Okay, by using this process, we are going to diagonalize some matrices and we are going to see the nature of the quadratic form. See, let us see the definition of quadratic form. A homogeneous polynomial of second degree is called the quadratic form. For example, if you have this x square plus y square minus z square minus xz minus 10yz plus xy equal to 0. Look at this, each term having the degree 2. Here it is degree 2, here it is degree 2, here this is degree 1, 1 plus 1, 2. Here also we have 1, 1, so therefore degree 2. Here also we have 1, 1, so therefore degree 2. Okay, then this is an example of one quadratic form, and then z square plus d square. This is another quadratic form. Then x square minus xy. This is another quadratic form. Look at this, all the terms having the degree 2. Okay, whereas here x square plus y square minus z square plus z minus y, this is not a quadratic form. Why? Because here degree 2, degree 2, degree 2, but here the degree is 1. Here the degree is 1. See, therefore this is not a quadratic form. This is not a quadratic form. Right. Next one, the canonical form definition. A quadratic form Q is said to be the canonical form if it has only the squared terms. Look at the previous example. We have x square plus y square minus z square minus xz minus 10yz plus xy. We have these combinations, right? Okay. This is not a canonical form, whereas this is a canonical form. Why? Because we have only two variables, z square plus d square. We have only a squared terms, but this is not a canonical form. See, therefore, the simplest example of canonical form is x square minus y square plus z square. This is one canonical form. Another canonical form is 10 z square minus 100 y square plus x square. This is another canonical form. We have all the terms which are squared term. So this is a canonical form. Right. So next we are going to see some basic definition regarding to the quadratic form, that is index, rank, signature of the quadratic form. What is the index? The index of the quadratic form is the number of positive eigenvalues of A. Number of positive eigenvalues of A, that is nothing but your index. And the rank of the quadratic form, which is nothing but the number of non-zero eigenvalues of the matrix A. And third one is the signature of the quadratic form is the difference of positive and negative eigenvalues of A. The formula is S equal to 2p minus R, where P is the index, R is the rank of the matrix. So next definition, the positive definite, positive semi-definite, all these things. Let Q, which is equal to X transpose A into X, be a quadratic form in n variables, x1, x2, and so on, xn. And A is a real symmetric matrix associated with the given quadratic form. Now first definition, the quadratic form Q is said to be positive definite if all the eigenvalues lambda 1, lambda 2, lambda n are positive. That is, all the eigenvalues of the matrix A are positive, then we can say the quadratic form is positive definite. In this case, the rank of the matrix will be n and index will be n. And the second definition, the quadratic form Q is said to be positive semi-definite if all the eigenvalues except 1 or 2, all the eigenvalues except few are positive. That means all the eigenvalues lambda 1, lambda 2, and so on, lambda n are non-negative, and at least one of the eigenvalues 0. At least one of the eigenvalues 0. Here in this case, the rank of the matrix is strictly less than n, and P equal to R. Next definition, negative definite. The quadratic form Q is said to be negative definite if all the eigenvalues are negative, the rank is n, and index is 0. Next definition, the quadratic form Q is said to be negative semi-definite if all the eigenvalues are non-positive and at least one of the eigenvalues 0. Here in this case, the rank is less than n and index is 0. If all the eigenvalues satisfies none of the above, then the quadratic form is called indefinite. Okay, right. So next, if you know all the eigenvalues of the matrix, by using the eigenvalues we can define the definiteness of the quadratic form. If you don't know the eigenvalues, by using the simple calculation of d1, d2, and so on, dn, we can able to define the definiteness of the matrix. Now let Q be the quadratic form given by X transpose into A, X, where A is a real symmetric matrix. Let us define d1 equal to the first element of the matrix. d1 is the first element, and d2 is the first 2 cross 2 determinant of the first 2 cross 2 matrix. What is d2? A11, A11, A12, A21, A22. Whose determinant? That I defined it as d2. Similarly, d3 is the first 3 cross 3 matrix determinant. A11, A12, A13, A21, A22, A23, A31, A33, A32, A33, and so on. And dn is nothing but your determinant of the original matrix A. Then the first definition, the matrix A is positive definite if all the d1, d2, d3, and so on, dn are positive. Okay. Then second definition, if Q is positive semi-definite, all the di's are non-positive, and at least one di will be 0. All the di's are non-negative. All the di's are non-negative, and at least one di will be 0. So negative definite means d1 is less than 0, d2 positive, d3 negative, d4 positive, and so on. If it happens, then the quadratic form is negative definite. If d1 negative, d2 positive, d3 0, d4 positive, and so on, then it is negative semi-definite. That means all the minus 1 power k into dk are non-negative, and at least one di will be 0. In this case, it is negative semi-definite. If none of the 4 above satisfied, then the quadratic form is indefinite. Okay, now let us see, let us classify the quadratic form, discuss the nature of the quadratic form given by q equal to 6x square plus 3y square plus 3z square minus 4xy minus 2yz plus 4xz. First we have to find out the matrix of the quadratic form, right. So as I said, A is a real symmetric matrix. First we place the diagonal entries. Here the first row is for x row, second row for y, third row for z. Similarly the first row for x, first column for x, second column for y, third column for z. Okay, what I am saying, this will be the coefficient of x square, this will be the coefficient of y square, and this will be coefficient of z square. That is 1/1th position is coefficient of x square, 2/2th position is coefficient of y square, 3/3th position is coefficient of z square. What is this position? This position is coefficient of x and y. Here also we have the coefficient of x and y. See, therefore, whatever the value we are having, that is a coefficient of xy, that should be divided by 2, and we have to place it here. Suppose if you have the coefficient of xy is 4, then we have to divide this number by 2, that is 2. You have to place 2 here and place 2 here. If it is 6, then you have to place 3 here, you have to place 3 here, likewise. What is this position? This position is coefficient of xz. Then find the coefficient of xz, divided it by 2 and place it here and here. Okay, this position is coefficient of yz. Find the coefficient, divided it by 2, place it here and place it here. Okay, clear? In this way we have to form the real symmetric matrix A. Look at this. As I said, A is a 3 cross 3 matrix. Why? Because there are three variables playing x, y, z. The first we have to fill the diagonal elements. The first 1/1th position is coefficient of x square, that is your 6. Let me put 6 here. Then 2/2th position is coefficient of y square, that is 3, put here. And 3/3th position is coefficient of z square, put here. What is this one? This position is coefficient of xy. The coefficient of xy is -4. See, therefore divided it by 2, that leaves -2. Put -2 here, put -2 here. Okay, and then here this position is coefficient of xz. The coefficient of xz is +4. Divide this by 2, that gives 2. Put 2 here and put 2 here. This position is for coefficient of yz. Coefficient of yz is -2. See, therefore divided it by 2. Divide this by 2. See, therefore you will get -1, -1. Okay. Anyway, there is a mistake here. I have taken this is positive. Okay, positives, that then only will be getting a positive one. Okay, so let me take this as a +2. See, therefore divided by 2, divided by 2. See, therefore we will be getting +1, +1. See, therefore the matrix is 2, -2, 2, -2, 3, 1, 2, 2, 3. Okay. Now what is our D1 now? D1 is the first element. D1 is first element. D2 is the determinant of the 2 cross 2, first 2 cross 2 matrix. 6, -2, -2, 1, therefore 14. And D3 is determinant of the original matrix, see, therefore 32. See, therefore look at this. D1 is positive, D2 is positive, D3 is positive. See, therefore the quadratic form is positive definite. Okay. Right. See, next example. Reduce the quadratic form into the canonical form by using the orthogonal transformation. That means the original transformation is having the variable x, y, z, but we have the combination x, y, y, z and x, z. Okay, therefore this is not a canonical form. Suppose if this is not there, then the given quadratic form itself a canonical form. But we have the combination, see therefore we have to reduce this quadratic form into the canonical form by using the orthogonal transformation. That means we have to calculate the matrix A and then the eigenvalues, eigenvectors, normalized eigenvectors, model matrix, okay, then n transpose A n, that gives the diagonal matrix, then we have to define the canonical form. Okay, these are the things involved in this problem. Now, the characteristic equation of the above matrix, let me define what is the matrix for this quadratic form. Look at this here, the coefficient of x square is 8, see therefore 8 here, coefficient of y square is 7, see therefore 7 here, coefficient of z square is 3, see therefore 3 here, and coefficient of xy is minus 12, see therefore divided by 2, minus 6, and coefficient of xz is 4, see therefore this is 2, then 2, coefficient of yz is minus 8, see therefore minus 4, here minus 4, okay. This is your matrix of the quadratic form. Right. See therefore the characteristic equation corresponding to this matrix A is lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0, and s1 equal to 18, s2 equal to 45, and s3 equal to 0. Okay, that means s3 equal to 0. See therefore the matrix is singular matrix. That means one of the eigenvalues will be 0. So if you replace s1, s2, s3 in the above general equation, we will be getting lambda cube minus 18 lambda square plus 45 lambda equal to 0, and evidently we see that lambda 1 equal to 0, and lambda 2 equal to 3, and lambda 3 equal to 15, and we have to find out the eigenvectors corresponding to lambda 1, lambda 2, lambda 3. Okay, so for the matrix equation A minus lambda into x equal to 0, first replace lambda 1 equal to 0, that gives the system of equation 8x11 minus 6x12 plus x13 equal to 0. Similarly, we are getting the second equation, third equation. What is our capital X1? Capital X1 is x11, x12, x13. Okay, right. If you take the first two equation and by using the cross multiplication rule, we found that x11 equal to 1, x12 equal to 2, and x13 equal to 3. So this is a formula which you have seen already. See therefore your x1 equal to 1, 2, 2, and then the length of the vector x1 is under root 1 square plus 2 square plus 3 square, that is equal to 3, and then the normalized eigenvector is 1 by 3, 1 by 3, and then 2 by 3, again 2 by 3. Similarly, for lambda 2 equal to 3, we are getting three distinct equations, 5x21 minus 6x22 plus 2x23 equal to 0, and second equation, third equation. By taking the first two distinct equations and by using the cross multiplication method, we get x21 equal to 2, x22 equal to 1, and x23 equal to minus 2. That is the second vector x2 equal to 2, 1, minus 2, and its length which is equal to 3. Therefore, the normalized eigenvector x2 bar equal to 2 by 3, 1 by 3, minus 2 by 3. Similarly, for the third eigenvalue lambda 3 equal to 15, we get the system of equation minus 7 x31 minus 6 x32 plus 2 x33 equal to 0, and the second equation minus 6 x31 minus 8 x32 minus 4 x33 equal to 0, and by using the cross multiplication method, we solve that x31 equal to 2, and x32 equal to minus 2, and x31 equal to 1, and its normalized eigenvector is 2 by 3, minus 2 by 3, and 1 by 3. Okay, now we got all the eigenvectors and its normalized eigenvectors. Now we are ready to define the model matrix N. Now the model matrix capital N is capital N, which is nothing but x1 bar, first column is x1 bar, second column is x2 bar, third column is x3 bar. Okay, so that is your first column is this, second column is this, and third column is this. Okay, now find the transpose. Luckily this matrix A transpose n transpose equal to n. See, therefore we have this n transpose, this is your A and this is your n. If you multiply these matrices, then you will be getting the eigenvalues in the diagonal, and the other elements will be 0. The first element is 0, second element is 3, third element is 15, and all other elements are 0. Right. See, this is your diagonal matrix. Now let us define the new vector x which is equal to n into y, where y which is equal to y1, y2, y3. See, therefore y transpose dy, that gives the quadratic form, the same quadratic form, that is your canonical form. Y transpose dy is your required canonical form, that gives 0 y1 square plus 3 y2 square plus 15 y3 square. If you know this diagonal matrix, then it is easy to define what is a canonical form. 0 y1 square and 3 y2 square, then 15 y3 square. Okay, so this is a required canonical form. From this canonical form, we see that lambda n equal to 0, lambda 2 equal to 3, and lambda 3 equal to 15. See, therefore one of the eigenvalues is equal to 0, hence, and other twos are positive. Therefore this is a positive semi-definite. Right. Now what is the rank? The rank is 2, because the non-zero eigenvalues are only 2. Therefore the rank is 2, and the index is the number of positive eigenvalues, that is also 2. Therefore the index is 2, and the signature is also 2. Okay. See, in this problem, look at this. In this problem, all the eigenvalues are distinct eigenvalues. Lambda 1 equal to 0, lambda 2 equal to 3, and lambda 3 equal to 15. All are distinct eigenvalues. See, therefore we were able to find out linearly independent eigenvectors x1, x2, x3, and then we were able to find out the normalized eigenvector x1 bar, x2 bar, x3 bar. See, therefore we computed the model matrix. Sometimes the eigenvalues may be equal eigenvalues. Look at this problem. Reduce the quadratic form 6x square plus 3y square plus 3z square minus 4xy plus 4xz minus 2yz into a canonical form by using the orthogonal transformation. Okay. Now the matrix of the quadratic form is 6 minus 2 2 and minus 2 3 minus 1 and 2 minus 1 3, and corresponding characteristic equation is lambda cube minus 12 lambda square plus 36 lambda minus 32 equal to 0. If you solve this quadratic characteristic equation, we get the eigenvalues are lambda 1 equal to 8, lambda 2 equal to 2, and lambda 3 equal to 2. Look at this, there are two eigenvalues are same. In this case, we have to use one definition that's called orthogonal definition. We'll see it later. If lambda 1 equal to 8, by using the above procedure, we find the eigenvector x1, which is equal to x11, x12, x13. Okay, just to replace lambda 1 equal to 8 in the matrix equation. Okay, and multiply this vector, you will be getting the equations like this. You take any two distinct equation, and then by using the cross multiplication method, we can able to find out what is the solution. In fact, x11 equal to 2 and x12 equal to minus 1, x13 equal to 1. So the eigenvector is 2 minus 1 1, and its length is under root 6. See, therefore x1 bar equal to 2 by root 6 minus 1 by root 6 and 1 by root 6. For the second eigenvector, use the usual definition, that is take lambda 2 equal to 2 and then replace lambda equal to 2 in the matrix equation. What is the matrix equation? A minus lambda I into x equal to 0. Here x is this vector. Replace lambda 2 equal to 2 and subtract like this, then you will be getting the equations like this. Okay, so look at this. This equation is if we replace lambda equal to 2, we'll be getting all the equations are same equations. That means evidently there is only one equations. Okay, see, therefore the equation will be like this: 2x21 minus x22 plus x23 equal to 0. So there are three unknowns: x21, x22, x23, but there is only one equation. See, therefore there are infinitely many solutions are available for the system, but among them we are going to choose one. So let us fix that x23 equal to 0. It is in our hand. Okay, we can fix x22 equal to 0 or x21 equal to 0. Okay, let me choose x23 equal to 0. If you choose x23 equal to 0, then x22 equal to 2x1, and if you fix x21 equal to 1, then x22 equal to 2. See, therefore the vector is 1, 2, 0, and its length is under root 6, and the normalized eigenvector is this vector 1 by root 6 and then 2 by root 6, 0. To find the third eigenvector corresponding to the same eigenvalue, value is same, that is 2, we have to use the orthogonal property. That means the vector x3 should be orthogonal to the other two vectors. Orthogonal means perpendicular. So we are going to find out the vector x3 such that it is perpendicular to x1 and x3 is perpendicular to x2. Okay, if they are perpendicular, then the inner product of these two equal to 0. That is a geometry. Okay, the geometry says that if any two vectors are perpendicular, then their inner product, okay, their inner product equal to 0. See, therefore the inner product of x2 and x3 is also 0. The inner product of x3 and x1 equal to 0. Okay, right. Let me fix x3 equal to x31, x32, x33 by using the orthogonal property x3 transpose into x1 equal to 0. This is the inner product. Okay, and x3 transpose into x2 equal to 0. This is called inner product. Okay, see, therefore the first equation is x31, x32, x33 with this column vector. We are getting this, which implies x31 equal to minus 2x3, 2x32. From this x31, from this vector, I mean the inner product, we are getting 2x31 minus 3 minus x32 plus x33. But already we have defined x31 equal to minus 2x32. See, therefore replace this x31 by this expression, hence we will be getting minus 4x31 minus 4x32 here. Okay, minus 4x32 minus x32 plus x33 equal to 0. See, therefore x33 equal to 5 times of x32. If you fix x32 equal to 1, x32 equal to 1, then x31 equal to minus 2 and x33 equal to 5. Therefore the third eigenvector is minus 2, 1, 5, and its length is under root 30, and the corresponding normalized eigenvector is minus 2 by root 30, 1 by root 30 and 5 by root 30. Now we have computed all the eigenvectors and normalized eigenvectors. Now we are ready to define the model matrix. Now the model matrix is this matrix, and to compute the diagonal matrix we have to use this definition, D equal to n transpose A into n. So this is your n, and calculate transpose means the row is converted as a column and the column is converted as a row, right? So this is n transpose A n, that gives the diagonal matrix 8, 2, 2. And by using the similar definition x equal to ny, where y equal to this column vector, therefore the canonical form is y transpose d into y equal to 8y1 square plus 2y2 square plus 2y3 square. So from this we see that all the eigenvalues are positive, so therefore the quadratic form is positive definite, and all the eigenvalues are positive, so therefore the rank equal to 3 and index equal to 3, so therefore the signature is also 3. Okay, see, fine. There are some exercises are given. you try these problems, and thank you.